Okay, let's wait another minute and then we begin. Okay, I think that we can start. It's a pleasure to introduce Marijana Butorac from University of Rijeka in Croatia, and she will talk about quasi-particle basis of standard models for affine algebras. So please, Marijana.
Okay, thank you, Lucia, for the introduction. I would also like to thank the organizers of this seminar for this opportunity to give a talk today. And I will talk about joint works with Slaven Kozic and Mirko Primc, which are related to these projects. Okay. So this research belongs to representation theory of affine Kac-Moody Lie algebras. We construct combinatorial bases of standard modules, which are examples of highest weight modules, by using the theory of vertex operator algebras. And from constructed bases, we obtained characters of standard modules. So my main plan for today is to give you some details about this construction. So during this talk, I will use the following three examples of affine Kac-Moody Lie algebras as the main examples in this talk. So on this slide, you can see two untwisted affine Lie algebras, one of the first one of type A11 and of type BL1, and the twisted affine Lie algebra of type DL plus 1, 2. So I will start with some basic notations and definitions. So to construct affine Kac-Moody Lie algebra, we start with a complex simple Lie algebra of type xn, and here n denotes the rank of a Lie algebra. So in the first two cases, xn will be either of type A1 or of type BL. So we tensor simple Lie algebra with a vector space of Laurent polynomials in variable t, to which we add two one-dimensional vector spaces spanned by elements C and D. So we get infinitive dimensional vector space, which I will denote by a symbol G tilde. So the same symbol I will use also in the case when simple Lie algebra is of type DL plus 1. So in that case, we will assume that on G is defined non-trivial automorphism. So this automorphism is induced from a Dynkin diagram automorphism, and I will use the same symbols for both automorphisms. So the Dynkin diagram automorphism fixes first L-1 vertices of Dynkin diagram and interchanges the vertex L and L plus 1. So we decomposed the simple Lie algebra of type DL plus 1 into eigenspaces of mu, which correspond to the eigenvalues plus minus 1. So in the first case, that is the eigenspace which corresponds to the eigenvalue 1 is isomorphic to simple Lie algebra of type BL, and the other eigenspace, so which corresponds to the eigenvalue minus 1, is isomorphic to irreducible highest weight module of simple Lie algebra of type BL with the highest weight omega 1. So this is just the fundamental weight of simple Lie algebra of type BL. Okay, so G tilde, this infinitive dimensional vector space, becomes a Lie algebra if we define Lie brackets in a standard way, so that the C becomes the central element and D becomes the degree operator. Here in blue, it is denoted the non-degenerate bilinear symmetric form defined on a simple Lie algebra. Also, I'll write xm for the elements of the form x tensor by t to m, where x is from G, and m will be an integer in the first two examples, and it can also be half integer in the third example. H tilde will denote the Cartan subalgebra of G tilde, and here H is the Cartan subalgebra of the corresponding simple algebra. So in all three cases, we will have the Cartan subalgebra of simple algebra of type BL, where L starts from 1. Lambda I denote the fundamental weights, and here alpha j check for every j denotes the simple co-roots which span the co-root lattice, and we also have q the root lattice. Okay, so now let lambda be the dominant integral weight, that is the linear combination of fundamental weights with positive coefficients. We will assume that lambda is of level k, positive integer, so that is the eigenvalue of the central element C. L of lambda, that is the standard G tilde module, or the integrable highest weight G tilde module, is unique up to an isomorphism, a highest weight module generated by a highest weight vector. It can be constructed as a quotient of a generalized Verma G tilde module, n of lambda. So that is, n of lambda is an induced G tilde module induced by BQ. So U denotes a finite dimensional irreducible module of a suitable simple algebra G with the highest weight sum of kj lambda j, which becomes a module of subalgebra of G tilde denoted by G tilde superscript greater or equal to 0 if we define the following relation. So every element of the form xn where n is greater than 0 maps all vectors from big U to 0 vector. Also, the degree operator maps all vectors to 0 vector, and C acts as a multiplication with a scalar k. The character of standard module L of lambda is defined as a generating a function of the dimensions of weight subspaces with respect to the chosen Cartan algebra H tilde. So for every standard module, we have a Veil-Katz character formula. So it is known that suitable specializations of this character formula can be given as infinitive products, and we can interpret these infinitive products as generating a partition function. So this suitable specialization, they provide a link between representation theory of affine algebras and number theory. So for the case of standard modules of affine algebras of type A11 and A21, and also for the case of principal specialization, which is related to the principal gradation of affine algebra G tilde, Lepovsky and Milne showed this fact. In particular, they showed that all standard A11 modules, so when they are principally specialized, are equal up to some factor to the product side of Gordon-Andrews-Bressot identities, which are generalization of Rogers-Ramanujan identities. So in particular, for the level 3 standard modules of highest weight 2 lambda 0 plus lambda 1 and 3 lambda 0, in this slide are written these principally specialized characters. So the factor which is common for both forms is the first factor, and it is actually a principally specialized character for all level 1 A11 standard modules, while the remaining products are product sides of Rogers-Ramanujan identities. So Rogers-Ramanujan identities are two analytic identities which are expressing infinitive products as infinitive sums. As a combinatorial Rogers-Ramanujan identities, we mean identities which are given by giving the combinatorial interpretation of the coefficients in a formal power series. Lepofsky and Wilson, they constructed a monomial basis of graded representations spaces for affine algebra of type A11 in terms of partitions which satisfy certain difference conditions, and they are related to Rogers combinatorial Rogers-Ramanujan identities. So they did it by introducing vertex operators as a tool for construction of level 1 standard A11 modules. This symbol in the end of the slide, we will think of it as a formal power series with coefficients Pm, which represent the number of partition of positive integer m in R parts. So we will use that during this presentation. Okay, so Lepofsky and Wilson, they provided a link between vertex operator algebras and number theory. Okay, they also initiated the so-called Z-algebra program. So Z-algebra are generalization of vertex algebraic structures for studying representations of affine algebras through vertex operators. As a part of that program, Lepofsky and Primc, they constructed a combinatorial basis of parafermionic spaces for all standard modules of affine algebra of type A11. So parafermionic spaces are quotients of standard modules, and very roughly speaking, we can think of them as vector spaces spanned by coefficients of parafermionic currents. So these coefficients they are acting on standard modules, and parafermionic currents, so again, very roughly speaking, we can think of them as a formal power series which don't satisfy the locality. So this is the property which is usual for vertex operators. So the first examples, as well as the notion of parafermionic currents in the two-dimensional conformal field theory, appeared in the work of Zamolodchikov and Fatev. Later, Gepner constructed a family of solvable parafermionic conformal field theories which were related to the untwisted affine Kac-Moody algebras at the positive integer levels. Lepofsky and Primc from constructed combinatorial basis calculated characters which were expressed in terms of Rogers-Ramanujan-type sums. And these characters were the same as characters conjectured by Kuniba, Nakanishi, and Suzuki. So Kuniba, Nakanishi, and Suzuki, they actually conjectured the characters of parafermionic spaces for all untwisted affine algebras. And Georgiev gave the proof of these character formulas for affine algebras in simply laced cases, so for the cases of A, D, and E. And we generalized the construction of Georgiev to the untwisted affine algebras of type B, C, F, and G. And later, Okado and Takenaka extended this construction to the standard modules with highest weight k lambda 0 for twisted affine algebras for all twisted affine algebras, and in a joint work with Slaven, we extended then this result and we proved the character formulas given by Gepner for the so-called rectangular highest weights in the twisted cases, so for twisted affine algebras of type 812-1 and DL plus 1. In this slide are written two formulas for parafermionic space for the case of affine algebra of type B21 with the highest weights lambda 0 plus lambda 1 and lambda 0 plus lambda 2. So they are written also in a Rogers-Ramanujan-type sum form, and they are obtained from our construction of parafermionic bases, and they are the same as Kuniba, Nakanishi, Suzuki characters. Okay, so our construction of basis of standard modules and also of parafermionic spaces has several steps, and the main step in this construction is the construction of the combinatorial basis of the principal subspaces. So now I will introduce principal subspaces and say something about their combinatorial basis. Okay, so let V denotes the highest weight vector of L of lambda, and we will fix the triangular decomposition of simple algebra G. So we fix the nilpotent subalgebra N plus, which is generated by root vectors which are corresponding to the positive roots of the simple algebra G. So we take the twisted or untwisted affinization of this nilpotent subalgebra N plus, and we define the principal subspace as a vector space generated by elements from the universal enveloping algebra of n tilde plus, which are acting on the highest weight vector. Actually, from Poincaré-Birkhoff-Witt theorem follows that principal subspace is generated by monomials from this vector space, which are acting on the highest weight vector. So here n tilde alpha I, where I goes from 1 to n, are affinization of one-dimensional subalgebras of simply algebra generated by root vectors which are corresponding to the simple roots. So the principal subspace can be defined for any highest weight G tilde module, but in this presentation, this talk, we will restrict ourselves to the rectangular highest weights, that is the weights of the form K0 lambda 0 plus Ki lambda I, where lambda I are level 1 fundamental weights. Okay, so the notion of the principal subspace was introduced in the work of Feigin and Stoyanovsky for affine algebra, for standard modules of affine algebra of type A11. Here is presented the basis of the principal subspace in the level 1 case with the highest weight lambda 0. So from the definition of the principal subspace, it follows that this universal enveloping algebra n tilde plus, that is n tilde alpha I, will be just algebra of polynomials in infinitive many variables. Since these elements do commute, we can arrange them so that they represent the so that their degrees decrease from right to left. We will also, from the definition of the principal subspace, follows that all of these degrees are less or equal to 0. And here with red, it is indicated that the minimal difference between two consecutive degrees is at least 2. So this is the so-called difference to condition. And this condition is related to the sum sides of Rogers-Ramanujan identities. So from this basis, we can actually easily calculate the character of the principal subspace. So in the case of the highest weight lambda 0, it is the sum side of the first Rogers-Ramanujan identity. And in the case of the highest weight lambda 1, it is the sum side of the second Rogers-Ramanujan identity. Okay, so principal subspaces were studied by many authors, and this is not the complete list of these people. Georgiev extended characters of Feigin and Stoyanovsky to principal subspaces, to the characters of principal subspaces of standard modules with rectangular highest weight for affine algebra of type AL1. Ardon, Kedem, and Stone, they actually generalized the Feigin-Stoyanovsky construction in order to obtain the character formulas for all integrable AL1 modules. And more recently, Kozic and Gardner, they connected characters obtained by Georgiev, so for standard modules of affine algebra of type AL1 with Warner-Zudilin conjecture in the context of superconformal field theory. Another circle of ideas came from the work of Caparelli, Lepovsky, Milas, and also from the work of Kalinescu, Penn, and Sadovsky. So they constructed exact sequences among principal subspaces of level 1 standard modules to find recursions satisfied by the dimensions of principal subspaces. And more recently, Zhao Li and Milas, they studied principal subspaces from the jet algebra viewpoint. So as I mentioned at the beginning, we construct a combinatorial basis of principal subspaces. So this basis following Georgiev, but also Feigin-Stoyanovsky's approach will be described in terms of quasi-particles. Okay, so to define the quasi-particles, I will just remind you that standard LK lambda, standard module LK lambda 0, standard module for untwisted affine algebra of type xn1 has a structure of vertex operator algebra, and it is known fact that every level K standard module of this untwisted affine algebra has a structure of irreducible module for this VOA. Heisenberg showed that every standard module of level K for twisted affine algebra has a structure of mu twisted module. So this is a concept which generalized the concept of module for VOA. Mu twisted modules are vector spaces equipped with a map, twisted vertex operator map, which maps vectors from LK lambda 0 into this formal power series with coefficients which are linear operators on V. And these twisted vertex operators, they do satisfy certain properties. Among these properties, in the construction of our bases, we mainly used the locality. So, which means that if we multiply vertex operators which are corresponding to the vectors u and v by this polynomial for t greater or equal to 0, then we can write these vertex operators in any order. So this property actually generalized the commutativity. Okay, so if we fix simple roots alpha I, then we can define a quasi-particle of charge 1 and color I and energy m as a coefficient of a vertex operator, which corresponds to the vector x alpha I minus 1, which is acting on the highest weight vector of LK lambda 0. So since these vertex operators do commute, we have also vertex operators of this form, xr alpha iz, where r is a fixed positive integer. So by a quasi-particle of charge r, color I and energy m, where m is a fixed integer, we mean a coefficient of this vertex operator. So we can think of quasi-particles as a sum of actually as a cluster of R quasi-particles of charge 1 with energies from m1 to mr, which are running through the set of integers in such a way that only the total energy is measurable. So this sum will always be a finite sum, since our quasi-particles will always act on the highest weight vector. In this slide is given just the definition of quasi-particles. In an analog way, we can define the twisted quasi-particles, but their integers, for our example of the twisted affine algebra, can have integers, can have energies which are half integers. Okay, so this is the main theorem of this part. Before stating the theorem, I will introduce the set BWL lambda. So let BWL lambda be the set of all polychromatic quasi-particle monomials of this form, colored with colors which increase from right to left, and with charges for each color which are decreasing from right to left, and we will put a restriction on the maximal charges of a quasi-particle. So charges of quasi-particle for each color will be always less than or equal to k alpha I, and k alpha I in our examples will be either k or 2k. And we will assume that energies of quasi-particles in this set BWL lambda satisfy certain conditions, and we will call these conditions initial and difference conditions. So by using monomials from this set, we were able to show that for any rectangular highest weight lambda, this set of monomial vectors BV, so where B is from this set BWL lambda, forms the basis for the principal subspace of affine algebras. So the proof of this theorem goes in two parts. So in the first part, we prove that this set is actually a spanning set by using the relations among quasi-particles. And in the second part, we prove the linear independence of this set. And this is done by using coefficients of intertwining operators as well as other operators which are coming from the theory of vertex operator algebras and are specific and are depending on the structure of affine algebra. Okay, I will try to explain these conditions, initial and difference conditions, using the following example. So in the case of affine algebra of type A11 in the set BWL lambda 0, so in the bases of principal subspace are quasi-particle monomials of this form. So by an initial condition, we mean that energy of every quasi-particle is less or equal to -1. So this follows from the definition of the highest weight vector, the definition and also the definition of the quasi-particles. While the difference condition is the so-called difference to condition. So, and this condition follows from Lipovsky-Primc relation for quasi-particles of charge 2, which states that every quasi-particle of charge 2 is equal to 0 on a level 1 standard A11 module. We use this relation in a way that we define a certain order among quasi-particles, and with respect to that order, we find the smallest monomial, and in this slide are given two examples of this smallest monomial. So these are monomials which have the same energies or that their energies differ for 1. And we exclude these monomials by representing them as a linear combination of higher monomials, and the higher monomials are exactly monomials which satisfy the difference to condition. Okay, in this slide are examples of quasi-particle monomials in the base of the principal subspace for affine algebra of type B31 for the highest weight to lambda 3. So in this example, quasi-particle monomial will be colored with 3 colors which correspond to simple roots alpha 1, alpha 2, and alpha 3. So the first 2 colors, the charges of the first 2 colors are less or equal than 2, while the charge for every quasi-particle of color 3 is less or equal to 4. So this follows from the relation which is analog to the previous one. So on a level 2 standard module, every quasi-particle of color 3 and charge 5 is equal to 0, and also every quasi-particle of color 1 or color 2 and charge 3 is equal to 0. As you can notice, these quasi-particles, they don't satisfy the difference to condition. Actually, they satisfy the generalization of a difference to condition. So when we have quasi-particles with higher charges, then we have to find the relation among quasi-particles of the same color but different charges, and these relations follow from the definition of quasi-particles. And also we have to find a relation which describes the interaction between quasi-particles of different color, and these relations follow from this locality. In the last example on this slide, we have a quasi-particle monomial from the basis of the principal subspace for affine algebra of type D42 with the highest weight 2 lambda 3. This quasi-particle monomial is colored with 3 colors, but in this case the highest charge for all 3 colors is 2. And again, the difference condition, they follow from the relations which are describing the interaction of quasi-particles of the same color but different charges, and quasi-particles of different charges, different colors and different charges. Okay, so to write the characters of principal subspace, we write the difference and initial conditions in terms of Pij. So here Pij denotes the number of quasi-particles of color I and charge J. And in this small example, we have a graphical representation of the charges of quasi-particle monomial. So in this example, we have one quasi-particle of charge 1, we have one quasi-particle of charge 2, and so on. And by rewriting difference conditions and initial conditions in terms Pij, we obtain the characters. So here is given the example for the affine algebra of type B21 with the highest weight lambda 0. And in the next slide, it is given the character formula of the principal subspace with the highest weight to lambda 3 for affine algebra of type B31. So here matrix G describes the interaction among quasi-particles. And here in red are indicated the parts which are coming from the initial conditions. So if we remove these conditions, these parts, these red parts, then we will obtain the character of the principal subspace with highest weight to lambda 0. In this slide, it is written the character of the principal subspace with the highest weight to lambda 3 in the case of affine algebra of type D4 again, we have matrix G, but it is different from the previous case, and again, in red are denoted the parts which are coming from the initial conditions. So if we remove this red part, then again we will get the character formula of the principal subspace with highest weight to lambda 0. Okay, now we will use a combinatorial basis of principal subspaces to obtain the basis of the standard module. So to state the main theorem for this part, I will start by introducing the set B prime W. So it is the subset of this set BWL lambda, but it contains all quasi-particles that doesn't contain quasi-particle monomials, that doesn't contain quasi-particles of maximal charge k alpha I, which again can be either k or 2k in our examples. With E alpha check, I will denote the Weyl translation operator, which acts on the standard module L of lambda. And by BU H hat minus, I will denote the Poincaré-Birkhoff with the type basis of the universal enveloping subalgebra of G tilde. So in the first row, H hat minus, it is written this subalgebra for untwisted cases. So here H again is a Cartan subalgebra of simply algebra. And in the second row, the bottom row, we have subalgebra H hat minus for twisted cases. So here H0 and H1 are eigenspaces of the Cartan subalgebra H with respect to the automorphism mu. Okay, so easily from the by using the combinatorial basis of the principal subspaces, we were able to prove that for any rectangular highest weight lambda, the set of all monomials of this form, so E alpha check, where alpha check is an element of a choroid lattice, H is an element from this Poincaré-Birkhoff with type basis set from the previous slide, and B is an element from the set B prime. So these monomial vectors form a basis of a standard module. So from this theorem. So using this basis, we can easily find the character of the standard module L of lambda. And in this slide, it is written only for rectangular highest weight lambda in the untwisted cases B, C, F, and G. So the first factor follows from the set from the set BU H hat minus. So it describes this contribution. The second factor follows from the combinatorial basis of the principal subspace, and the third factor actually follows from the contribution of the action of Weyl translation operator. Okay. In the case of affine algebra of type B3-1 with the highest weight to lambda 3, this character formula is written in this way. Now, as you can see, we have a matrix G prime, which is of order 5, so it has 5 rows and 5 columns, and in this example we had 8 rows and 8 columns. So this follows from the fact that this monomial from this set B prime are in the basis of the standard module. Again, in red is the note, the parts which describe the initial condition which are satisfied by the elements in the basis. This is for the case B31, and this is the formula for the affine Lie algebra D42 for standard module with the highest weight to lambda 3. And again, this red denotes the part which is coming from the initial conditions on quasi-particle monomials. Okay. So along with principal subspaces, there is another type subspace, another subspace of a standard module. It is the so-called Feigin-Stoyanovsky type subspace, which was introduced and studied by Primc for all standard modules of affine algebra of type AL1. So in the case of affine algebra of type A11, the definition of the principal subspace is actually equal to the definition of the Feigin-Stoyanovsky type subspace, and we can define the sequence of these subspaces of a standard module with the highest weight lambda 0. Here E alpha to the n denotes the composition of Weyl translation operators which are acting on the principal subspace with highest weight lambda 0, and by taking the inductive limit when n goes to infinity of this sequence, we can obtain the whole integrable highest weight module of this highest weight lambda 0. So this was done by Feigin and Stoyanovsky for all standard A11 modules, and also for Primc for all standard AL1 modules. And motivated by these results, Primc, Baranovic, Jerkovic, and Trupcevic, they constructed a combinatorial basis of the Feigin-Stoyanovsky type subspaces for standard modules of untwisted types, and we tried to to construct Feigin-Stoyanovsky type subspaces in the case of twisted affine algebras. So first, to define the Feigin-Stoyanovsky type subspace, we have to fix a minuscule weight of a simple algebra of type dl plus 1. So this will be the weight such that it is invariant under the action of the Dynkin diagram mu. So this weight defines the z gradation of a simple algebra of type dl plus 1. So here G note denotes the reductive Lie algebra, and G plus minus 1 are abelian subalgebras of G. So we will take the twisted affinization of G1 and we can then define the Feigin-Stoyanovsky types space as a vector space spanned by monomials from this universal enveloping algebra of G tilde on mu, which are act on the highest weight vectors. So this algebra is commutative. Which means that our quasi-particles will commute, but to construct the basis of Feigin-Stoyanovsky's type subspace, we will only consider quasi-particles of charge 1. And the colors of these quasi-particles are described by this set gamma. So here are just used the elements of the standard basis of L-dimensional Euclidean space. So I goes from 1 to L and represents the elements of this basis, and root vectors x1 0 and 1 underline 0, they represent the projection the projections of root vectors which are corresponding to the root 1 L. So it is actually root of the form alpha 1 plus alpha 2 plus and so on until alpha L plus 1. So projection on the subspaces of G1 with respect to the automorphism mu. In the from Poincaré-Birkhoff-Witt theorem follows that elements in Feigin-Stoyanovsky's type subspaces are of this form x pi v, where x pi are monomials of this form. So we have colors gamma I, where I goes from 1 to L plus 1 from the set big gamma. And we also have degrees j, and AI and BI represent the frequencies which count the number of times that energy J appears in the partition with a given color I. So we will say that the monomial x pi satisfies the difference condition for level k if his frequencies satisfy these conditions. So we have a lot of these difference conditions, but they follow from the relations between twisted vertex operators on a standard module for twisted affine algebra of type dl plus 1, 2. And these relations are a generalization of relations which was obtained by Bajranović in the untwisted case dl plus 1, 1. So we first use these relations to show that monomial vectors which don't satisfy difference conditions from the previous slide can be excluded from the Poincaré-Birkhoff-Witt spanning set. And in this example, it is presented a graphical sketch of difference condition which are not satisfied by the monomials in our spanning set. That means that we excluded these monomials. So we have monomials colored with color gamma and gamma prime, and with the same energy. So these monomials are excluded from our spanning set. Also monomials colored with color gamma and gamma prime and with energies m and m prime, such that the minimal distance is either 0, 1/2 or 1. So we exclude these monomials, and to the given set we add monomials which satisfy the initial conditions, which are written for level k and also for level k is equal to 1. So this basically means that if we have two monomials with energies -1/2 and -1, then they are not in our spanning set. We exclude them because they don't satisfy the initial condition. We've showed that this set is actually a linear independent set, again by using some specific operators from the theory of vertex operator algebra, and also from the theory of twisted vertex operators. Only for the case of level 1 standard modules with the highest weights lambda 0 and lambda L. So this is the result connected to the affine algebra of type DL plus 1, 4. And in the last part, I will just try to explain how we obtain the basis of the parafermionic spaces. So we start with the principal subspace. We find the combinatorial basis of these subspaces. Then we use these combinatorial bases to find the basis of the standard module, and then we use the obtained basis to find the basis of the parafermionic space. I will start by introducing the vacuum space of the standard module L of lambda. So it is a linear span of all vectors from the standard module, which are annihilated by the elements Hn, and here H is an element from the Cartan subalgebra and n is a positive integer. So Georgiev defined the parafermionic space of highest weight lambda as a space of KQ coinvariants of KQ module omega L of lambda. So here rho K alpha denotes the action of abelian group KQ, so which is isomorphic to the group Q, the root lattice, and on this space we also have a defined canonical projection. So this definition relies on the lattice vertex operator algebra construction of level 1 standard modules in A, D, and E cases, which is not the case for untwisted affine algebras of type B, C, F, and G. So we define the parafermionic space of highest weight lambda for these cases as this union of gamma weight subspaces of vacuum space omega L of lambda. So here gamma is an element of this abelian subgroup KQ of Q, and K alpha I are again K or 2K, and in the case of affine algebra of type G to 1 they can be also 3K. So following Georgiev approach, we define the parafermionic projection, and by using this projection we were able to show that this set of monomial vectors forms the basis for the parafermionic space in the case of affine algebras of type B, C, F, and G. Here again B prime W denotes the subset of of BW. So it contains quasi-particle monomials, which doesn't contain quasi-particles of maximal charge. And we were able to extend this theorem to twisted cases A2L minus 1, 2 and DL plus 1, 2 for rectangular highest weight by extending the result obtained by Okado and Takenaka. So I will explain, at least try to explain these basis monomials. To do that, I will define the parafermionic current of charge n as a composition of these two operators which are acting on the highest on the vacuum space. So here Z and alpha Z denotes the Lepolsky-Wilson's Z operators, which are defined by using the vertex operators of charge n and color alpha. And here E plus and E minus are just these formal power series. So first we take the monomials from the basis of the standard modules, and by using this projection with a superscript h hat plus, we project them to the vacuum space. So this means that the elements of the vacuum space basis will be of this form. E gamma B prime V, so where gamma is from the root lattice and B prime is a monomial in the coefficients of the operators of charge n. And then by using a parafermionic projection, we find the images of these basis elements. So elements in the parafermionic space basis will be of the form B2 prime V. So here B2 prime is just a monomial of the operators, so the coefficients of the parafermionic currents, and here V denotes the image of the highest weight vector with respect to the parafermionic projection. So we showed that these basis elements are eigenvectors for the operator L omega 0, which is coming from the work of Haisheng Li on the generalized vertex algebras. And we calculated the values of these eigenvectors, and from that we obtained the characters of parafermionic spaces. And again, here in red are indicated just the parafermionic shifts, meaning that these parts, they don't appear in the character formula of a standard module. And I will end with an example of a character of parafermionic space for the case of affine algebra of type B3(1) with the highest weight to lambda 3. So this is all. Thank you very much for your attention.
Thank you very much, Marijana. And are there any comments or questions? Okay. If not, we can thank again Marijana, and we can meet the next time for the next seminar. Thank you, everybody.
Thanks.
Bye, Marijana.
Bye.